Okay, so in the last lecture, the last pre-recorded lecture, we went over 1.8 and 1.9. Today we're going to go over section 1.10. So what in 1.9 we went over, we went up a dimension. We were originally thinking about the real line and subsets of that. And then in 1.9 we introduced the coordinate plane. We started thinking about subsets of that, and then graphs of the subsets, like how do we plot these subsets, and then also graphs corresponding to equations. Because it's not always the case that if you have a set that it's, and you graph the set, that it's the graph of some equation. There's not always the case. So every equation gives rise to a graph, but not every graph arises as the graph of some equation. So that's a point to keep in mind. But in section 1.10, we're going to specifically look at a particular type of equation, a line, and then we're going to look at the graphs, but something which we're probably already pretty familiar with, but we'll just go over this anyways and maybe formalize some ideas. So let me share my screen. All right, so this is section 1.10, and it's 1.10. Hold on. So section 1.10, and this is on lines. So we all have an idea of what a line is, but we want to associate an equation to a line. So this, if you can graph a line, and this is an example of something which has a corresponding equation. So this is an example of a graph which has a corresponding equation. So let's derive this equation. So first of all, we need to talk about the steepness of a line. So if we have our coordinate plane, we have maybe this line going through here. We want to talk about like the steepness of this, sort of this angle even relative to the x-axis. And so we call this steepness the slope, and it's simply the rise over the run. And this will actually end up just being the change in y over the change in x. And what do we mean by that? Well, to get the slope, you need 2 points on the line. So if you take a point here, so let me get rid of this symbol here. So if you take 1 point on the line keeps, whoops, that's good enough. And you take another point, you can calculate the slope. So the slope, so we tend to call the slope, or denote the slope as m. And so the change in y is the difference in the y coordinates of these 2 points over the distance, the difference in the x coordinates. So these 1s and these 2s attached to these y's and x's, these are the indices. So 1 and 2 are indices, or a single one is an index. And you want to be careful of the indices. So look at, if you have this 2 here, then you have the 2 that goes here. There's this correspondence. You don't want to mix and match these indices at all when you're calculating this. So the first problem that might arise is, well, how do we know that this like really uniquely, the slope is sort of unique in some sense to the line? What if I chose a different pair of points? Would I get a different slope? And that is a legitimate worry, but it turns out that we don't have to worry about that, and for a reason I'm going to point out right now. So let's just draw that line again. So suppose we take 2 different points. So we'll start with our same points again here, and then they form a triangle. So we have x1, y1. Then this is let's see, So yeah, we have x1, y1, and then over here we have x2, y2 for this point. And then now we take different points here. They form this triangle. And then we have x1 prime, y1 prime. And then over here we have x2 prime, y2 prime. So we can use this, we can use these pair of points here to calculate a slope. But then we can also use these pair of points right here to calculate slope. And so the question might be, well, why does this give you the same slope? And the reason is that these two triangles are similar. They're similar triangles. So what it means is that if you take this length right here, which is the change in x, so this will be this length right here will be x2 minus x1, and then this length right here will be y2 minus y1. If you take this ratio here, it's going to be the same as the ratio of these lengths. But that's by definition the slope of a line. So this length right here, the length of this side is x2 prime minus x1 prime. And then the length of this side of the triangle is y2 prime, y1 minus y1 prime. And so because these triangles are similar, they have this angle right here is the same, right? If they have the same angle, all the angles are the same, actually, I should say. And then this is right. Oh, this is maybe they might actually, these are not necessarily the same angles. The theta 1 and theta 2 might be different, but the corresponding angles are the same. So this theta 1 right here is the same as this theta 1, and this theta 2 is the same as this theta 2 up here. And then, of course, they both have this 90-degree angle right here. So these are similar triangles. So the triangles are similar. So what that means is that the ratio of their sides, so this ratio right here, is equal to this ratio right here. So what this shows is that slope is independent of choice of points. So it is truly an invariant of the line in some sense. And what this means is that as long as the points are on the line, you can choose any two pair of points and you'll get the same slope. So the problem that we initially arose of whether or not this definition of slope was well defined is just simply evaporates because we showed that it's independent of the points you choose. So this will help us actually determine the equation of a line. So just I'm going to point some slopes that you can possibly have. So maybe I'll say possible slopes. This will give you different shapes of the line. Not shapes, but just angles at which they're oriented. So this first one you have something like this. This corresponds to a positive slope. So your slope is positive. You could have a line that goes down like this. This would correspond to a negative slope. You could have something like this. This would be a zero slope. Well, and the reason why is that if you take 2 points on this line, the change in y is 0 because the y coordinates of these 2 points are the same. So the overall fraction is 0. So this will have a 0 slope. And so this is a horizontal line. And finally, you could have a vertical line. And this is no slope, or you would say, in this case, you would say there's no slope or it's undefined / undefined. It just does not have a slope because the change in x is 0, and you can't have division by 0. So you can't have a slope for these lines. So now that we have this notion of slope, we can, which is a measurable quantity, you can just find that angle and get the slope. We want to talk about point slope formula, or the point slope form of an equation. So suppose, here's the setup. Suppose you're given a line, and you know it passes through a point, some point x1, y1. And and it has, its slope, m. So m is, so this is some point in the plane. This is some slope you're given. It's a fixed number. You don't, it's already given or determined for you. Well, we want to find out other points on the line. So we'll just say let x comma y be some arbitrary point, just any point on the line. It could be this point given, or it could be some other point. So it's just some arbitrary point on the line. Well, because the slope, so if that's the case, we can calculate the slope, right? We can say y minus y1, x minus x1 is the slope. But slope is independent of choice of points. We just determined that by the similarity of triangles. So what this means is that this fraction right here, is just equal to m. So we have y, so this implies that y minus y1 over x minus x1 is equal to m. And then we can actually solve the equation. So we just multiply. Actually, we do want to stipulate that x is not x1. So maybe it would be a good idea not to choose the same point. So we want to choose some other point, which would make sense. We want to choose a different point, actually. We don't want division by 0. So erase this. So we can solve for this, and then what we'll obtain is y minus y1 is equal to m times x minus x1. And then we can simplify this further by adding y1 to both sides. So this will give us, this y1. This will now completely determine the line. So now just remember the setup. The setup is that you're given a point that it passes 0, and you're given the slope. As soon as you're given these pieces of data, these two pieces of data, you can completely determine the line. And again, it relies on that fact that the slope is a sort of invariant of the line, that it doesn't depend upon what choice of points you use to compute it. It'll always be the same. That's what allows us to do this right here, to say that m equals this fraction right here. That invariance of the slope allowed us to conclude that these two things have to be equal. So let's look at an example now. So this is example 2 in the book, and it's find an equation. Really, it's going to be the equation because it's uniquely determined by this data. So find an equation of the line through the point 1 minus 3 with slope -1/2. So in our case, we have x1, y1 is equal to 1, -3, and m is equal to -1/2. So we can use this formula right here to determine the line. So what we'll have is y is equal to -1/2 x minus 1, and then plus y1, but y1 is equal to -3. So this is one way of writing it. You can also put it in the so-called, this is point slope form. So you can also put it in the standard form. And that looks like this. You actually just throw everything on one side of the equation. So we're going to distribute the negative through, -1/2 through. So we get -1/2 x plus 1/2. Well, actually, no, what we're going to do is multiply both sides by 2 to get rid of the fraction. Oops. So that will give us 2y is equal to -x minus 1 minus 3, or sorry, 6. Then we'll distribute the negative through to get -x plus 1 minus 6. And then we can throw everything on one side. So we can add an x to both sides. So we x plus 2y. This 1 and -6 combined to give you 5, but we're going to put it on the other side, so it'll become plus 5 over here. And then this will be equal to 0. And this is your standard form. But I don't know how important that will be. But I thought I'd just point that out. So there's also an example, and I won't go through the whole example, but sometimes you're not given the point and a slope. You're given 2 points. But this is really just almost a special case of what we just did. So find an equation of the line passing through the points -1, 2, and 3, 4. Well, to do this, you just first get the slope. So the slope will be, so I could say that this is x1, y1, and this is x2, y2. It doesn't matter. I could have labeled these the opposite way, just so long as I'm consistent with my labeling. So it's going to be the change in y, so it's y1 minus y2, so it's -4 minus 2. And then the change in x, so it's x2 minus x1. So it's 3 minus -1, so that becomes +1. This will become 6, -6, and this will be 4. And this will become -3/2. So at this point, we're pretty much done. We can determine the line because now we have a slope, m. We just determined that. This is our slope. And we have a point. In fact, we have 2 points on the line. So we could choose either one and go through the same process that we did here in this example 2 to determine the equation of the line. So if you're given 2 points, it's not much of a more hassle. You just got to get the slope first, and then you can put that in point slope formula using either this point paired with this slope or this point paired with this slope. Either one will give you the same answer. So the next thing, this is point slope formula. There's another form of the equation. Sometimes you're given different data. So the next thing you could have is maybe a slope and an intercept. So this is the slope intercept form. Maybe you're not given the slope and a point, but you're given a slope and intercept. This is actually just a special case because the intercept is a particular type of point. So this is a slope intercept form of the equation of a line. So this is just a special case of the slope point formula, because the intercept is a particular point. On the line. So suppose you have slope m and y-intercept. So we're given the y-intercept b. So the point in the plane corresponding to this point, this intercept is 0b. This is a point on the line. So for example, maybe you have something like this. This would be your point 0b here. So suppose you're given just, all you're given is the slope of this line and this point right here. You can still determine the equation of the line. So in this case, if you remember our formula is y is equal to m times x minus x1 plus y1. So in our case, x1, y1 is equal to the point 0b. So if I plug all of that in, and of course m is given also. So we're given this point and we're given this slope right here. If I plug in this point right here, I get a simplified version of this point slope formula. So when your equation of the line is in this form, you can directly read off the slope and the intercept. M is always going to be your slope, and this will always be your y-intercept right here. So when it's in this form, you can easily read off the slope and the intercept. So let's see now. Okay, so there's some examples, but they're pretty easy. I won't go over them unless you want me to. You can have a look at them yourself, and if you find them confusing, we can go over them. So I just want to point out a couple more things. So we spoke about vertical and horizontal lines before. So what are the equations of these? So we have these vertical and these horizontal lines. How do we find these equations? Well, if a line is horizontal, then we know its slope m is 0. So if you go back to the equation, so we have y is equal to m x minus x1 plus y1. If you plug in 0, what you get is y is equal to y1. So it's constant. The y coordinate is constant. And this kind of makes sense, is if you draw the graph of a horizontal line, let's look at that. Let's make sure this syncs with our intuition. If you draw a horizontal line, so this is y equals y1. If you take any point, so right here on the y-axis, we have this point y sub 1. And if you take any other point on here, the x coordinate is changing because you got this is the x coordinate of this, x coordinate of here, x coordinate here, and here and here. The x coordinate is changing, but the y coordinate is not. The y coordinate is always y sub 1. But what about a horizontal line? Let's draw a horizontal line and try to figure this out. What's the equation of this? Well, a vertical line. If you have a vertical line, suppose this vertical line goes through here at x sub 1. If you take any point along this line, the y coordinate is changing, See? The y coordinate is changing, but the x coordinate is not. So y is in some sense free to be whatever number you want, but x has to be x equals 1, always. So this will be the equation of this vertical line. So a vertical line will always be something of the form x is equal to some number, say x1 or a or b or whatever. And a horizontal line will be something of this form. It'll be y is equal to some fixed number, y1, say. So now let's look at the last thing in this section. I think it's the last thing is parallel and perpendicular lines. So let's look at parallel lines first. So suppose you have, this is our setup here. So you have this line, and this line. It's clear, like if you draw out this angle here, so slope is roughly like the angle it makes with the x-axis. So if you were to take this line right here and kind of shift it down this way to an overlay on this one, you notice it has the same slope. So what this shows is that non-vertical lines which are parallel have the same slope. In fact, this is an if and only if. So, and the idea basically follows from this idea of similar triangles. I won't go through the proof, but there's a proof in your book. But the idea follows from the similarity of these triangles. If you draw these, if you choose 2 points on here, on each line, and you draw these triangles, you'll find that these triangles are similar. So that they have to have the same slope right here. So this angle will be equal to that angle, but that angle corresponds to, these angles being the same correspond to them having the same slopes. So for parallel lines, we have 2 non-vertical lines, such as we have here. Are parallel if and only if they have the same slope. For perpendicular lines, we have another nice fact. I'm not going to try to justify this though, because it's a little trickier. Proof is a lot more involved. So I'll just state the fact, and if you want, you can look at the proof, and we can, if it doesn't make sense to you, maybe we can try to figure out what's going on there, but you're not required at all to know why exactly this is true. So we have that 2 lines, with slopes M1 and M2 are perpendicular if and only if the product of their slopes is -1. And this can just be rephrased equivalently as saying that M1 is equal to -1 over M1. So the perpendicular just means that they cross at a 90-degree angle. So if you maybe have this line going like this, something like that. And then let me try my best to draw this perpendicularly. So this angle right here, well, it's supposed to be a 90-degree angle. It's not exactly. But this, they kind of meet at a 90-degree angle right here, or they're supposed to meet at exactly a 90-degree angle. That's what it means for these to be perpendicular. And you can, if you know the two lines are perpendicular, you know that their slopes have to satisfy this equation right here. So let's go over just two examples, and then we'll call it a day. So let's do something with parallel lines first. So this is example 7 in the book. So we're asked to find an equation of the line through the point 5, 2 that is parallel to this line. So that's 4x plus 6y plus 5 is equal to 0. So we want to put this in point slope form. So we have to, and then once we know the slope of this line, we'll know the slope of the line we're interested in. So let's find that first. So we got to solve for y. So we'll subtract 4x from both sides and 5. And then we'll divide by 6. So if we divide by 6, we get negative 2/3 x minus 5/6. So this implies that our slope is 2/3. The slope of this line is 2/3, but the slope of the line parallel to this is also 2/3. So we have, so what this means is we have a slope, namely negative 2/3, and a point, namely 5, 2. And then from here, we can just use the point slope formula to get the line, the equation of the line that we're interested in. And so I won't go through that because we already did 2 examples like that. Now let's do example 8. So example 8 is about perpendicular lines. No, wait, sorry. No, so example 9. So the example is, or the question is, find an equation, or what we're asked to do is find an equation of the line that is perpendicular to this line, the equation represented, the line represented by this equation, 4x plus 6y plus 5 is equal to 0, and passes through the origin. So the origin, you'll recall, is represented by the ordered pair 0, 0. So we have a particular point on the line. Now we just need to find the slope to this line, and we're done. To do that, we first find the slope of this line that we're told is perpendicular to it. So, well, actually, hold on. This is just the one we did up here. So we're told, we know that this line has a slope of negative 2/3, right? But remember, so this will be M1. We want to find, or need to find, M2. Well, we know that M2 is equal to negative 1 over M1. So that implies that M2 is equal to negative 1 over negative 2/3. And if you simplify that, you flip the fraction, you cancel these negative signs and flip it, you get 3/2. So again, we have a point, namely 0, 0, and a slope, namely M2, which is equal to 3/2. And then we can just do point slope formula to get the equation of the line and we're finished. So that's all for today. And just make sure you're reading the sections, you're watching these videos so that you can come to me with questions on Friday. So we'll actually have something to do. Otherwise, we won't do anything, I guess. So that's all for now.